And so we're going to finish off our discussion of solids and liquids today by asking what happens when you do in fact heat a solid. And finally, to close our discussion of solids, suppose we take a chunk of something, some solid, stick a thermometer in it, and begin heating the stuff up. What are we going to see happen? Well, at first what's going to happen is simple. The temperature is going to go up. That's simply a specific heat problem. You add energy to the solid will go up in temperature. But then you're going to hit a point where even though you continue to heat the stuff, the temperature doesn't change. It just levels out. And it's going to level out for a while. And it's just going to go along at that same temperature, and then suddenly at some point the temperature will start going up. It'll be going up with a different slope than it had before. And again, that'll go along for a while. The temperature will go up and up and up, and then again it will stop going up. And even as you continue to put heat in, the temperature won't change. And it won't change for a long time. It takes a long time for this to get over it. And then finally, all of a sudden, the temperature will again start rising sharply. So what's going on? Well, like we said, the three places where the temperature is rising are straightforward. They're specific heats. But they all have different slopes, which means they have to have different specific heats. But what's going on in the plateaus? What's obviously going on in the plateaus is a phase change. The solid, changing the solid into a liquid, melting, requires energy. And so as long as the solid is melting, the energy is all going to melting the solid. Nothing can go up in temperature as long as any of the solid is left, because the phase change has priority. And so even though you're heating the stuff, as long as some of it is still there to melt, the temperature won't go up. Once you've melted all the solid, of course, you simply have the liquid, and its temperature starts going up, but it'll have a different specific heat than the solid did. When we talked about specific heat of water being 4.184 joules per gram degree C, that's for liquid water. Ice and steam have different specific heats, because of course that's the next thing that's going to happen. We're again going to get a phase change. The liquid is going to turn into a gas. And of course, that's going to take energy. And in fact, it's going to take a lot more energy. It's a lot easier to get the molecules in the solid into motion, that is to turn it into a liquid, than to pull the liquid apart against the intermolecular forces and turn it into a gas. And so the second plateau is much longer than the first one, because it's going to take a lot more energy to boil the liquid into the gas phase than it was to simply melt the solid. And again, it's a plateau. As long as there's any liquid left, the phase change has priority. All the energy goes into boiling the liquid into the gas. And finally, once all the liquid is gone, then again the temperature can go up. And this, of course, is going to be the heating curve for anything. It's going to have specific heats that are different for the solid, the liquid, and the gas, and the plateau for the evaporation is going to be much larger, much longer than the level for melting will be. And that concludes our discussion of solids. We can now move on to our next topic, which is kinetics. Consider these three reactions. What do these three reactions have in common? Well, they're all combination reactions. We're starting out with elements and forming compounds. Specifically, we're starting out with elements and reacting them with oxygen to form compounds. And each of these reactions is in fact an exothermic reaction. The compound is lower in energy than the reactants, and so we get heat released. That's what they have in common. What is different about them? Well, the first one, of course, is just iron reacting with oxygen to form iron oxide. In other words, rust. And how long does it take an iron nail left to itself to turn into rust? Well, left to its own devices, it'd take years. That's why they use iron nails to build houses, because this reaction, of course, all by itself is extremely slow. The second is carbon reacting with oxygen to form carbon dioxide. And carbon, of course, is basically charcoal. That's what charcoal is. So when you light up a charcoal briquette, how long does it take the charcoal briquette to become carbon dioxide? Well, that one's faster. Probably takes about 45 minutes to burn a charcoal briquette to CO2. The last one, of course, is hydrogen and oxygen forming water. And there are at least two conspicuous examples of hydrogen and oxygen forming water. One from the 1920s and one from the 1980s. The first one, of course, is the Zeppelin, the Hindenburg, which blew up and spectacularly burned in New York. The one from the 1980s, of course, is the Challenger space shuttle, which also blew up. And how fast were those reactions? Well, they were clearly over in seconds. So what's the difference between these three reactions? What's obviously different is how fast they are. The first one is almost incredibly slow. The second one is moderate. The final one is very fast. We haven't actually worried about how fast reactions are up till now. All the reactions you've seen done in laboratory were, of course, designed to be very fast reactions so that the experiment could be done during the lab period. But the fact is, some reactions, while some reactions are extremely fast, other reactions are spectacularly slow. And so we have to start talking about kinetics. That is, how fast does the reaction actually run? And so we can start talking about the rate of the reaction. A rate is simply the change of some quantity divided by time. So if we looked at a nice simple reaction of a molecule of A reacting with a molecule of B to form two AB molecules, we could look at it as the change in concentration of A versus time. And if we set the experiment up, mix the A's and B's together, what would we see? Well, what we would see is the concentration of A would, of course, plunge quickly to start with. But then it would start curving away. The rate of the reaction would change. And why is the rate of the reaction changing? Well, the reason the rate changes is fairly simple. The requirement for A and B to react is they do in fact have to collide with each other. They have to be in the same place at the same time. Not in the same beaker or test tube, the same place at the same time. They actually have to collide. Well, to start with, when the concentrations of A's and B's are high, it's fairly easy for them to find somebody to react with. And so initially the reaction goes very quickly. But as the reaction runs, we're using up A's and B's. The remaining A's and B's in solution are going to take longer and longer to find somebody to react with, which means the reaction is going to run slower. Because keep in mind, are the A's and B's in solution looking for each other? And the answer is no. They're just wandering around. And they have to sort of wander around until they collide with somebody. And as the concentrations get small, that's going to take a longer and longer time. So the rate of the reaction is going to change over time. It's going to slow down because there are simply fewer collisions. So obviously the rate of our reaction depends on the collisions. So when looking at our rate, it's going to have a concentration dependence on A and B. And those concentrations are going to be raised to some exponent. We talk about the order of the reaction. Well, why is there an order of the reaction? Well, we said it depends on collisions. If we start out with a container that contains two A molecules in the gas phase, what are they doing? Well, they're moving around and they're bouncing off the walls, and from time to time they will collide with each other. They will, in fact, have collisions. What would happen if we doubled the concentration of A? That is, put in 2 more particles of A. Would that double the number of collisions? Well, no. Initially, the A only had the other A to run into. Now it has 2 more A's to run into. And so is its collisions going to double? No, it's going to more than double. In the same way, the second A originally could only collide with the first A. Now it's got 3 that it could collide with as well. So its collisions is going to be more than double. And finally, of course, the 2 A's we just added weren't colliding with anybody to start with, so all the collisions are new for them. And so, in fact, doubling the concentration didn't double the number of collisions. It ended up a whole lot more than that. And this is what we see. Changing the concentration of some of the reactants can have an exaggerated effect on how fast the reaction runs. And so we have to take those concentrations and raise them to some exponent. We talk about the order of the reaction. In a first order reaction, the x would be 1. In a second order, it would be 2, etc. What else would the rate of our reaction depend on? Well, you have to keep in mind, A and B are molecules. And why are they molecules? They're molecules because the A's are bonded to each other. The B's are bonded to each other. Before we can produce products, that is the ABs, we're going to have to break both of those bonds. And that's going to take energy. And so if we have a diagram of the energy of the reactants and the products, what we see is the A's and B's start on the left and end up as the ABs on the right. And in this case, it's an exothermic reaction because the ABs are lower in energy than the A and B were to start with. But in between, we're going to have to put energy in. We're going to have to break the bonds between the A's and between the B's before we can make molecules out of them. And so we talk about an activation energy. It's the energy we have to put in to make the reaction take place. And so it has the effect of forming an energy barrier between the reactants and the product. We see that the rate of the reaction is going to depend on how big this barrier is. If it's a small barrier, it's very easy for the reactants to get over it, and the reaction should be very fast. If it's a moderate barrier, then some of the reactions will work and some of the collisions won't, and the reaction will be somewhat slower. If it's a large barrier, then very few of the collisions will actually be able to produce products, and the reaction will run very slowly. And so to our rate law, we're going to have to add a constant, that is, a rate constant. The rate constant is basically a fraction. It indicates what percentage of the collisions between A and B actually have enough energy to get over the barrier. Well, that depends, of course, on how much energy A and B have to start with, and that, of course, depends on their temperature. So it's important to keep in mind that the rate constant for a reaction is going to be temperature dependent. Raising the temperature will make the reaction run faster because more particles will be able to get over the energy barrier. Cooling the solution off will tend to reduce the rate constant as a smaller fraction of the particles have the energy needed to get over the barrier. And that concludes our discussion of kinetics for today. Have a nice day.